All right, hi everybody. My name is Clayton Hickey and I'm going to be speaking about electroencephalogram. I'm going to do this in a series of short 10 to 15 minute talks. So let's get started. All right, EEG electroencephalogram was first reported in the 20s. The primary report came from Hans Berger and he coined the term electroencephalogram. The interesting thing for Berger at the time was that what he was recording voltage potential from scalp surface, but it didn't look anything like action potentials. At the time, people understood what action potentials were. They were these instantaneous electrical signals. But what he actually saw was this oscillatory rhythm. So what we've got illustrated here on the bottom is a sinusoidal wave at 10 hertz. And what Hans Berger first recorded in a young boy with EEG electrodes was this oscillatory rhythm, this 10 hertz rhythm from brain activity. And people really didn't buy it. People thought that he must be recording some sort of noise from his equipment. They really didn't understand how brain activity could have this oscillatory rhythm. And Hans Berger himself actually figured that the brain was sending signals. He was a firm believer in telepathy, and he figured that this signal he was recording was actually brains communicating directly with other brains, which is, of course, nonsense. Very smart guy, but a nonsensical perspective on telepathy. All right, so what is this signal? It doesn't look like action potentials. It is this oscillatory signal recorded at the scalp surface. And in order to understand what this signal really is, we have to start with some really basic electrical principles. The first principle is the idea of voltage, electrical pressure. And I'm just going to very briefly describe this in terms of analogy. The best way to think about this is that voltage is electrical pressure or electrical water pressure. If you have water in a pipe that is under pressure, this creates the potential for the water to flow through the pipe. And that potential sits there and is resident in that pipe, even if there is no flow through the pipe itself. You can measure the water pressure even when there's very little flow, okay? You also have current, which is the flow itself. And the analogy here is water flow itself, right? A measure of current is conceptually the same as a measure of how much water is currently flowing through a pipe. And then you have resistance, which is the conductivity of the medium in the system. And the analogy here, of course, is that some pipes will allow more flow, right? So a large, wide bore pipe is going to allow lots of water to flow, whereas a water filtration system, for example, where the pipe is full of porous charcoal, will let less water through. You can also think about this that a longer pipe takes more water pressure to put water through it, just as a longer piece of wire takes more voltage in order to create the same current flow through that resistor. Ohm's law is a very important principle that creates a relationship between these three constructs. And Ohm's law simply states that voltage is equal to current multiplied by resistance. So we can calculate voltage from a measure of current flow through a medium when we know what the resistance is of that medium. And the analogy here, of course, is that you can calculate the water pressure in a pipe from a measure of how much water is flowing through that pipe when you know what the diameter, the resistance of that pipe is. I'm also going to very briefly mention another measure because it sometimes comes up when people talk about EEG, and this is impedance. For our purposes, impedance is equivalent to resistance. When resistance changes over time, things become a little bit more complicated in terms of the underlying physics. And it is the case in EEG systems that resistance is not constant over time, so you get this variation in resistance. That means that we can define a better characterization of the resistance of the system, and we call that impedance. But don't worry about it too much. Impedance effectively refers to resistance for our purposes. Okay, so enough about electricity. What is EEG then? Well, the best guess of what EEG is when we record it from scalp surface is a reflection of the graded postsynaptic voltage potential that's created by the release of neurotransmitters. Now, many of you might kind of get what I'm talking about here, but I thought I'd very briefly review this concept. Neurotransmitters attach to receptors, right? So if we have a terminal button of a cell and we get something that happens here, proteins release neurotransmitters, they cross the synaptic cleft, they bind to receptors on the postsynaptic cell and the dendrites of the postsynaptic cell. And as a result, we get this opening of ion channels, and ions start to pass the cell membrane. Ions are cells that are either missing an electron or have too many electrons. So when they cross over the cell membrane, they create a voltage potential in the postsynaptic cell. They change the voltage in the postsynaptic cell. Because of this pump, more atoms with too many or too few electrons end up inside of the neuron. The electrons want to move from dense areas to sparse areas, but they can't, because once they're inside of the cell, they can't pass back through the ion channel. The cell wall insulates the flow of ions across the cellular surface. So the cell acquires a voltage potential. It becomes a little battery storing an electrical charge. And when the charge at the dendrites reaches a threshold, it triggers an action potential. But what we actually seem to be recording with the EEG is this graded postsynaptic potential. And I say graded because it can take many different values. That's in contrast to an action potential, which is an instantaneous charge of a certain known voltage. The PSPs, the postsynaptic potentials, can take a variation of many different values. And that seems to be what we see in the EEG. Okay, so let's think about this again. We have axons from presynaptic cells. They come down, they release neurotransmitters, and as a result, you get this opening of ion channels and this accumulation of, say, negative charge in the dendrites. As a result of the accumulation of this negative charge here, right, we actually end up with positive charge over on the other side of the cell. Relatively speaking, the dendrites become more negative than the positive charge over here on the body of the cell itself. And this defines a small battery, effectively, right? Now we have negative charge on one pole of the battery, positive charge on the other pole of the battery, and electrons want to resolve this difference between the poles. So we have now this accumulation of voltage, this electromotive force, where electrons want to transfer between the poles of this tiny little battery, but they can't. So there is this force encapsulated in this tiny little battery. That creates a field, right? There is now this voltage field that's created, and the field is not uniform. The greatest possibility of electrons sort of transferring between these poles, the greatest strength of the field is in the most direct route between the two poles. But if you go farther away, you get a reduction in the voltage field, but there still is a field. There still is the potential for electrons to flow as you go farther away from this direct route. And the water analogy holds here again. It's like when you have the most direct route between a river is the most direct route, but if you block the river, then you'll see the water take more indirect routes to resolve that difference, to resolve the difference between elevation in the case of water and rivers, all right? I wanted to make a quick observation here, and that's that the electrical field that's created by a current flow is orthogonal to the magnetic field. And this relates to the old right-hand rule that you probably learned about in physics in high school. If you have current flow, you take your right hand, you curl your fingers around. If you have current flow that follows your thumb, you will get electrical fields that follow that thumb, and you will get magnetic fields that wrap around orthogonal to that current flow. And that means that when you record EEG from the same brain activity, you will get a completely different pattern of voltage potential than when you record magnetoencephalogram, which is the magnetic field created by the same activity. You will have an orthogonal magnetic pattern. These two patterns will be directly opposite to one another, completely orthogonal to one another, because the magnetic field is orthogonal to the voltage field. All right, so the current flow created by one cell is going to be really tiny. But if many, many cells happen to have the same orientation, have the same reactivity, get the same input, then the current flow will be large enough that we can detect it at scalp surface. So we don't have to go inside of the brain to record this voltage field. We can actually put an electrode outside of this field and record it from scalp surface. And it happens to be the case that in cortex, many areas of cortex contain what are known as pyramidal cells. And these cells are known as pyramidal cells because the cell body has this sort of pyramid structure. They happen to be oriented orthogonal to scalp surface, to the surface of cortex, with the dendrites near the top of cortex, right? So these are the dendrites of these cells. And that means that when you have many, many of these all lined up, you will get this sort of organization where the negativity of activation of these cells will be close to cortical surface. The graded postsynaptic potentials here in the dendrites will be close to cortical surface. When many of these all line up, all of these fields will summate to create an appreciable field that you can measure from the surface of cortex or just outside of the surface of cortex on the scalp surface. If we put an electrolyte into this field, right? An electrolyte is purely a conductive solution containing positive and negative ions. It's mostly just salt and water. We put this electrolyte into the electrodes using a blunt-tipped syringe here, right? So these are the individual electrodes on the scalp surface, and then we goop a gummy solution of salt and water into these locations, so that now we have a metallic electrode inside of a solution of electrolyte that's connected to scalp surface. The voltage potential of underlying brain activity are going to push charge onto the electrode because this electrode is sitting inside of this field, this voltage field. If we subsequently ground out that electrode by connecting a wire to that electrode, we will get current flow through that wire into our measurement system, right? So the voltage field will induce current flow in the electrode, creating appreciable current flow that we can measure. Now, because of Ohm's law, if we have known resistance of this measurement system and we have appreciable current flow through the wire, we can infer the voltage potential at the electrode location. And that fundamentally is what EEG measures. We figure out what the voltage potential is at the location of the electrode, and we try and figure out from that the underlying brain activity in the brain space. The voltage is going to be very, very small because we're looking at a tiny little battery, so we'll need to amplify it up to be something big enough to look at. And then we're going to have to convert it from this analog signal, this analog voltage signal. We convert it to numbers. We use an analog to digital converter, which just purely puts that into a sampled frequency. So now we're sampling this analog signal at certain durations, converting it to a digital signal, and that digital signal we can store in a computer. I wanted to make the point that we're not always so lucky. It's not always the case that cells all line up orthogonal with cortical surface in the same sort of way so that the electrical field summates and is appreciable at the surface of scalp. These are those pyramidal cells which tend to have this sort of orthogonal orientation with the dendrites at the top of cortex, but we have other types of cells in the brain that do not have this same organization, and these do not create electrical fields that we can measure from the scalp surface. You have this, for example, in the cerebellum, where you have these Purkinje cells. These should be very good cells for what we want, in that all of their dendrites are close to cortical surface, the cell body's in the middle and this long axon. These should be good cells for recording of EEG, but it happens that the cerebellum itself is heavily folded. So this orientation is all mixed up, and that makes electrical activity from the cerebellum relatively hard to measure at scalp surface. So the tight folding in this brain area means that the electrical fields don't summate. The fields cancel one another out. I just want to make this point to kind of get the idea across that the recording of EEG is particularly good for some brain areas and worse for others. It's also the case that, of course, there are deep brain areas. So you have, for example, medial prefrontal cortex, or these structures that are subcortical, deeper in the brain. And electrical fields, the voltage field, as you go farther and farther away from scalp surface with the source of the activity, becomes harder and harder to measure. So EEG is also problematic for the recording of deep brain structures. You do see some activity in EEG that reflects activity in these deep brain structures, but it's much smaller and harder to identify than cortical activity. Thanks very much.